Welcome back. In this tutorial, we will begin our chase to find various solutions and algorithms that can estimate our integrals. The category of algorithms discussed here belong to the stochastic methods, where random numbers are the most important ingredients. I'll be providing detailed foundational information behind these methods and an overview of 3 sampling methods. As such, I do have dedicated tutorials on these 3 methods that provide more in-depth explanations and proofs. However, the high-level explanation that I am providing in this tutorial should be good enough for the purpose of this series. You will find the related content in chapter 11 of the book by Dr. Bishop. That said, let's first have a very quick recap. In part 5, we had gone over the most important constructs in Bayesian modeling, that is posterior distribution and posterior predictive distribution. And even though the Bayesian formulation of model is very intuitive and elegant, it suffers from the computational problems because of the various integrals that we now must solve. In part 7, I introduced you to a concept called conjugate priors. These conjugate priors enable the possibility to work around the challenge of computing integrals by choosing prior distributions such that the result is a known posterior distribution function. For these known functions, we know how to compute the normalizing constant using an analytical expression. But at the same time, this approach only works for very limited scenarios. And more importantly, just because conjugate priors helps us get analytical solutions, we should not use them if they are not the correct choice for our model. Now, let's talk about the subject of today. And since the integrals that we are chasing are primarily about computing the expected values, it would be a good idea for us to start by having an agreement on how we read and write its components. Expectation or expected value of random variable is nothing but a weighted average. Here I am showing you the general formulation for the discrete random variables first. The distribution that our random variables belong to are indicated using the symbol p with the subscript theta. Theta essentially represents a vector that is the parameters of your distribution. We also use this p symbol on the left hand side as the subscript of e, where e stands for expected value. And this represents the probability or weightage of the realization of the random variable. The symbol h represents the function of the random variable. Note that I always put the probability distribution function on the rightmost side. So the first comes the function of random variable, which is h of x, and then would come the probability distribution function, which is p of x. For continuous random variables, the difference is that instead of summation, we have an integral. This all being out of the way, the main challenge when it comes to computing expectations is that it is an integral from negative infinity to positive infinity. And for discrete, it is from 1 to infinity. And the remedy for this challenge lies in using a law called law of large numbers. This law simply states that if we can conduct large number of trials and if we can sample from our distribution, then we can approximate the expected value using a simple average. You can see that in this equation. But let me explain this with a simple example to build the intuition behind this law. So consider you have a fair dice and you are interested in its expected value. Since the possible states are only 6 and it is a discrete random variable problem, we can use this expression directly. Also, for this example, the function of our random variable, that is h of x, is nothing but just an identity function. That is, it simply returns x. We also know the probability of each state in a fair dice, that it is going to be 1 over 6. Essentially, all the states are equally likely. With all this information, it is very straightforward to apply our expectation formulation. You can see that we have used the h of x, which is simply giving you the value of the random variable, and p of x, which represents the probability of each state or the weightage of each state. And this evaluates to a value of 3.5. Clearly, in this example, the mean value of 3.5 is the theoretical value. You are not going to say that when I roll a dice for a long time, the average value is going to be 3.5. It's a theoretical value. But so far we have used our expected value formulation, but the big question here is that can we solve it using the law of large numbers? Which means that we should simply roll the dice many times and accumulate the numbers and then compute the mean value. And this is what I'm doing here. This plot is showing that as the number of rolls of the dice is increased, the running average starts to match the theoretical value of 3.5. The theoretical value of 3.5 in this plot is shown using the dashed horizontal line. So essentially, if you can sample from your distribution, you have a way to get the expected value without computing the integrals. This sounds pretty cool, huh? But it is quite uncomforting at the same time. Random numbers to solve a problem, it's bizarre. At minimum, you should start to have few thoughts related to this law of large numbers. First and foremost, how many number of samples do I need to have an unbiased estimate of the mean? If I try to do it again, if I repeat the process, would I still get the same estimated value? Or will it be different from the value I got in previous trial? And if it is different, how different it will be? You see, there is a reliance on randomness. So you would not always get the same expected value every time. But quite frankly, the most important question here is, how do we even sample from the desired distribution? Now, while these first two questions are legit and I would answer them at one point in the series, but for now really we just focus on the question number 3, which is about how do we even sample from our desired distribution. Here is a simple rephrasing of this question to make it hopefully more clear. Essentially, we intend to generate random numbers in accordance with the distribution. If this rephrasing is still not making the problem clear, then let me explain it with the help of a visual. Consider this function. This function represents a distribution that we want to sample from. This function is my attempt to replicate this picture that appears on the cover of classical book on Monte Carlo methods by famous Robert and Casilla. When I say in accordance with the distribution, it means that the random number of samples should be generated in proportion to their respective plausibility. What does it mean? So look at the area that is marked as red between 0 and 1. Clearly you can see that it's a high density zone. The value of the function here is higher than the other places. So more samples should come from here in comparison to the tails of this distribution. And now let's assume that I have an algorithm to generate samples from this distribution, and if I build the histogram, it would look like this. Histogram is essentially that I would have collected many number of samples and then I would have counted them. And this histogram, as you can see, looks very much like the geometric shape of our target distribution function. And this is what we want to do. This is what we want to achieve when we say that I want to generate a random number in accordance with the distribution. As such, you know how to generate random numbers using the programming language of your choice. This is how you would do it in Python, and it would essentially generate numbers between 0 and 1. You can of course scale these numbers to configure the range you desire. However, what you need to understand or know is that your computer only generates uniform random numbers. Uniform means that all random numbers between the desired range are equally likely. They have the same plausibility. These random numbers are also designated as pseudo-random numbers. Now the word pseudo means fake, but I must tell you that there is nothing fake about them. A proper name for these type of random numbers could have been deterministic random numbers, and they are generated or sort of controlled by what you use as an initial seed, amongst many other things. As such, my background is in security, cryptography, and embedded software engineering, and I was kind of enticed to explain how underneath random numbers are generated, but after some thought I figured that I'll be wasting your time if I do so. In brief, these so-called pseudo-random numbers are generated using few different algorithms, and you be rest assured that they are properly implemented and tested by your language and its standard library. This being said, if my computer, or rather the standard library of my programming language, can only generate uniform random numbers, what is the big idea here? And the big idea is the way you think about them. The way you want to think about is that these uniform random numbers are somehow being transformed in such a way that they seem to have come from your target distribution function, or they seem to follow your target distribution function, or they come in accordance with your target distribution function. There are many ways you will find this kind of a sentence written in the literature, but they all mean the same thing. And you also have a variety of these transformations and algorithms. Now I'm going to provide you a brief overview of 3 such algorithms. These algorithms, they differ from each other in their capabilities, efficiencies, limitations, and use cases as well. So let's start with the simplest of them, called InverseCDF Transform. The idea behind this algorithm is based on a theorem called probability integral transform. This theorem simply states that for any continuous random variable, you have a transformation that gives you standard uniform distribution. Standard uniform distribution has a range from 0 to 1. It's a uniform distribution, but the range is fixed to 0 and 1. Mathematically, you represent it like this. X is your continuous random variable. It has a distribution. And f represents the transformation function, which in this case is actually cumulative distribution function of random variable x. Now, unfortunately, if you do not know what CDF is, then this would not make sense. And for that, you may want to watch the full tutorial on this if you are interested. Y, of course, represents the standard uniform distribution. That's what this theorem is telling us. So, this is the fact stated by probability integral transform, and in my detailed tutorial on this subject, I show you the proof of this. Now, given this relation, and since we already have the support to get random numbers from uniform distribution, if I have the inverse of the CDF, the inverse function of the CDF, then we can get our random variable x. So probability transform is saying that you can convert any continuous variable to a uniform, and we are saying here that if we have the inverse of the CDF, then we can take we can take the standard uniform distribution and convert it to the random variable that we desire, or to the random number that we want to generate. So because there is a function involved, there is a transformation that is happening here. But the key is that you must have an analytical form of the inverse of CDF, my friend. Without it, there will be a problem. Let me show you this with a quick visual example. In the detailed tutorial, I built all this from scratch, but here is a quick summary. On the left hand side is the probability density function, and on the right hand side is its cumulative distribution function. In this case, fortunately, we have the inverse of a CDF. It's a very simple PDF, and computing this first CDF is possible, and then computing the inverse of CDF is also simple. And you can see that the y-axis of this CDF has a support from 0 to 1, which is same as that of a standard uniform distribution. So what we do is that we simply get a sample from the uniform distribution, use the inverse of the CDF, and we will get X, the sample, in accordance with its PDF. This all being said, this algorithm is indeed very limited because first and foremost, you need to have a CDF for your probability density function, and if you do not have CDF, you are in trouble. And the reality is that you do not have CDF for all the distributions. And even if you had a CDF, it does not necessarily have an analytical inverse of the CDF. Point is that it is a very fast method, but restrictive in the sense that it cannot be applied to all distributions. Let's see what rejection sampling is all about. This is the same function that I had shown you earlier from the cover of Robert and Casella. The equation represents this function that I have plotted. Now pay attention to this part. So one of the common theme that you would encounter in these sampling methods is that if you cannot sample from your target distribution function, then you use another distribution function to sample. And then apply a criteria to accept or reject the sample. This another distribution function from which you sample is called proposal function. First time you hear this, it sounds bizarre, but it does work, and at the same time is also the source of inefficiencies and the pain associated with this category of methods. So we have to use a proposal function now. And obvious choice for now, at least at the moment where we are, is that maybe we should just simply use the uniform distribution as the proposal function because we already know how to sample from it. Our language and standard library provides the support already. So here is the uniform distribution function, the proposal function, represented using green color, but it must be scaled to cover the entire support of your target distribution. Now, next thing what we do is that we sample from this proposal function. And this sample should fall between -3 and 3, including both of the numbers as well. So let's say that we did that and we got a sample indicated using orange X in the plot right now. And our task is to make a call on whether we should accept it or reject it. Note that it is indeed a valid sample for our target distribution because it falls in the support of the target function. But we need a criteria that should help us accept it in accordance with its plausibility. Now, at minimum, here what we can do is that we can pass this value of this sample to both our functions, that is f of x and g of x. The place of its functional evaluation for our target function is shown using this blinking pink marker. So the big idea behind this algorithm is that we are going to generate yet another random number, which I have shown using the symbol U. Look on the left hand side, there is new term that has appeared. This another random number is generated using uniform distribution. However, pay attention to the range of this number. It is now between 0 and g of x, where g of x is scaled using a constant c. What is important to pay attention to is that now we'll generate a random number and it will fall on this evaluation line. Also note that this evaluation line is shorter below the blinking marker in comparison to the portion above the blinking marker. For this example, for this orange X that I have generated, if this orange X was little bit on the right, you would see that the portion below the blinking marker would have been bigger than the one above. So if we are using a uniform distribution to sample our U, it is evident that more samples will fall on the portion above. So even though uniform distribution is going to give all the samples equally likely, but because of the nature of our evaluation line, the line on which you see the blinking marker, more samples are going to fall on the portion on the segment of the line above the blinking marker. Therefore, if this random number, this new random number U, falls below the blinking marker, then we will accept it, else we will reject it. This procedure, interestingly, has given us a criteria that allows us to record or keep samples in accordance with their plausibility. But do not forget that this criteria itself relies on random numbers and is the source of inefficiencies. Here is shown the source of inefficiencies. You can appreciate here is that to apply our criteria, we'll be generating random numbers, and majority of them are going to fall in the region marked as rejection region, because it's the evaluation lines that we will end up drawing, they will have a bigger portion falling in the rejection region. So one remedy is to use a proposal function that has a reduced rejection region. Why not? Here I am showing you such a case of selecting a function, a proposal function. In this case, it's a Gaussian function. But then you will ask or wonder, how do we sample from Gaussian function? And for that, there is a dedicated algorithm called Box-Muller algorithm. I'm not describing it here, but you will find it in the book by Dr. Bishop. It is relatively easy to understand as it is deterministic transformation of uniform distribution, and it is quite efficient. Main point here is that you can see that the rejection region now has significantly reduced. So to effectively use rejection sampling, you need to understand the geometry of your target function. Select an appropriate proposal function and then scale it such that it covers the entire support of your target function. This method is also limited to low dimensional probability distributions, and more importantly require that the target distribution is normalized. So you can imagine that in our Bayesian inference problems, most of the time our problematic part have been the denominator, that is, it is not normalized. So it will be very hard to apply rejection algorithm in those scenarios. So this was rejection sampling. Now we talk about importance sampling. As such, the name of this method is a misnomer, as it primarily is used to compute expected values rather than estimating the densities, which most of the sampling algorithms tries to do. If you think about it, our main task in Bayesian inference is to compute expectations. Posterior predictive distribution is an expected value. So this is an attractive algorithm for us as such. In the detailed tutorial on this algorithm, I describe three main types of problems that it addresses. First and foremost, dealing with situations when you cannot sample from the target distribution. Second is about a situation where you can sample, that is, you have an algorithm for your target distribution, but it is very inefficient for the problem you are trying to solve. I talk about the problems of rare event probabilities with an example and how importance sampling presents a solution for that. And the third one is about a variant of importance sampling algorithm that can deal with situations where you do not have the normalizing constant. Clearly describing all these situation scenarios and examples is a full dedicated tutorial. So here I provide you the essential background that should be good enough to build a decent high-level understanding. And for that, we need to bring our expected value formulation in the focus here. So assume that you cannot sample from P, that is the target distribution, and therefore you cannot apply the law of large numbers. As I mentioned earlier, one common theme in these sampling methods is that if you cannot sample from your target function, then you should take help from another distribution called proposal function. And of course, you need to accommodate for the fact that your sample is coming from a different function. So our main job here is to somehow introduce a proposal function in this expected value formulation. This is a time we have to be little crafty. And we do this by modifying the expected value formula like this. The symbol Q represents the proposal function. Since we are choosing it, of course, we'll choose the one from which we can sample. As you can see that this ratio is equal to the value of 1, and it is also known as probabilistic 1. More importantly, introducing this in our expected value formula is not going to change the outcome, as it really equates to 1. Now the next trick is that we switched the places between the target and the proposal functions. And because of this switch, you should start to see your expected value formula from a different view. You should treat Q as the function from which you sample. I hope you recall the conventions I established for expected value at the start of this tutorial. The rightmost term is reserved for the distribution from which we sample. And therefore, we should also change the subscript of E to reflect this. This also means that our function of random variable has also changed, and we indicate that using this new function called h prime. Since we now have the possibility to sample, we can apply our law of large numbers. This is very elegant if you think about it. The ratio of target function and the proposal function is known by few different names, but the one that suits the most in this context is called importance weight. It is essentially the correction criteria for the fact that we have used a proposal function for sampling. Now, unlike rejection sampling, there is no rejection notion. However, you must select the proposal functions carefully, and that is the hardship associated with this algorithm. Selecting the proposal function depends on the geometry of your function of random variable and original target distribution function, and also the type of problem you are solving. Check out the detailed tutorial if you are interested, in which I provide few concrete examples and their solutions using importance sampling. As such, there are few different variations of rejection and importance sampling. Importance sampling is widely used and is a huge topic by itself. And this was the essential review of Monte Carlo methods that I wanted to provide. But why these sampling methods are called Monte Carlo methods? For that, I need to tell you a quick background story behind it. And it is a story of Polish-American nuclear physicist and a mathematician named Stan Ulam, and a card game of solitaire. Stan Ulam used to work at Los Alamos Laboratory in New Mexico. New Mexico is a state in the United States where atom bomb was invented. And as the story goes, he was hospitalized and was trying to figure out a game of solitaire called Canfield, and he was interested in figuring out the chances that a Canfield solitaire laid out with 52 cards will come successfully. This is essentially a big combinatorics problem. You see, when these great scientists are sick, they are just wondering about other problems to solve. And he concluded to use a more practical method based on random numbers. He then shared his thoughts with his colleague, John von Neumann, who is undeniably one of the most important computer scientists in history. And Stan, Neumann, and many others in their team valued this idea of using random numbers in simulation on computers that they were building. And as a joke, Neumann suggested to use the name Monte Carlo for it. Now, Monte Carlo is the name of a casino in Monaco. Monaco is a tiny country on French Riviera where apparently Stan's uncle had lost a lot of money. And since this method of Stan had randomness or chance involved, and gambling also involves the notion of chances, they named it Monte Carlo method. But interestingly, their colleagues also took this idea further and solved things from differential equations to many problems in physics and ended up inventing one of the most important algorithms called Markov chain Monte Carlo. And this brings us to the end of our tutorial today. It is bizarre that randomness can be used for obtaining numerical results and construct criterias. I hope I have provided you enough background and overview of key sampling methods. However, you must note that these methods work well when certain constraints are met and when we have a finer understanding of the geometry of our target distributions, and more specifically when we are in low dimensional realm. That said, it would be interesting to have sampling methods that work for a wide variety of target distributions, and there is a category of such Monte Carlo methods called MCMC, Markov Chain Monte Carlo methods. The methods originally invented by the colleagues of Stan and John von Neumann at Los Alamos. In the next upcoming tutorials, I do intend to talk about these MCMC methods. And with this, I end the tutorial for today. I hope this was helpful and useful. Please let me know in comments if you have questions and need further clarifications. I thank you for the time you spent here and wish you good luck with your learnings. Thank you and goodbye. Bye-bye.